Hello, everyone. Welcome to Happy Hour with Architects. Today, we will talk about a very exciting topic, systolic arrays. Systolic arrays have been proposed and designed around 1980. However, it was way ahead of its time. Then it came back again in 2015 with Google's Tensor processing units. And literally, it has changed how we think about accelerators at the end of Moore's law. So today, I'm really excited to have two legends of systolic arrays with us today. H.T. Kang is a professor at Harvard University. He has pursued a variety of research interests, but he's the main architect behind systolic arrays, which he has invented while he was a professor at CMU. He also built the work machine for vision workloads in 1985, which had a linear systolic array. Our second guest is Cliff Young from Google Brain. He is one of the designers of Google's TPU, and he brought back systolic array after decades in hiatus. Before joining Google, he also built Anton supercomputer at D.E. Shaw. Welcome to both of you. Thank you so much for joining us today.
All right. Thank you very much, both of you. Nice to talk to you.
So thank you so much. So first, I would like to know about how systolic array started and what was the behind story and how HT actually came up with the idea. And then I guess we will go to Cliff to know about his personal journey around it. So HT, would you like to share the personal story?
Thank you for the opportunity. Actually, you really brought me back about a half century. This is a very interesting story I can tell you. And it's like back to the future. Okay, you can think about the past. Actually, you can invent the future. Let me try to explain to you. Okay. It's a beautiful story, actually, especially it was done when I was young. Kind of remember your youth, okay? So I was doing this with Charles Lyserson, who now is the professor at MIT. He was one of my earlier graduate students, one of the first one, very smart, obviously. And we were looking at that time, the serial automata was kind of hot. Later on, kind of didn't get anywhere, but for a while was people paying attention to that. We were just wondering maybe you should extend the serial automata to more general computing, not just to live games, stuff like that. To play some games or play something really simple. You actually do some computation, serious computation. So that's how we start realizing you can do matrix multiplications in a way so that the nodes, the cells are actually doing real applications of computation, not just doing a bit operation, doing a multiply accumulator, for example. So this was the beginning. Then the good thing about that time was the field is very exciting in general. Like this famous book by Mead Conway, Introduction to VLSI. Seems people have a lot of imaginations at that time. And that actually was a very good time, because this time was really the fabulous design kind of was started in a serious way. Now we know this is the mainstream now. in making chips, you use fabulous methods. And so Mead Conway kind of liked this. So we put this result in the chapter, in one of the chapters of the book. And other very good people at that time who recognized the importance of the thing is Irving Reed and several other leaders. Irving Reed, you probably know that name, is the Reed-Solomon code guy. Since that time, I've become a good friend of him. I went to USC several times talking about all this stuff. And the bit serial stuff is very interesting at that time. We now see all this AirPod earphones, stuff like that. That kind of stuff was envisioned in 1970s. People knew this thing was going to happen. You use the good bit serial implementation can do that. Systolic array is a very close to bit serial way of doing things. The concept is very similar. Actually, systolic array probably was known for 100 years. Similar kind of things been known for a long time. I later on kind of started realizing probably one of the real values of systolic array is the fact that each data you bring out from the memory can be used multiple times directly on the hardware, not going through the registers and back and forth and so on. You just go from cell to cell, of processing element to processing elements. So this I/O view is really important. I kind of start realizing that's really probably more important even than the regularity of those processing elements. Processing elements, it should be regular. We know that, of course. SIMD is always a grade of processing elements. So regularity is a small part of it. The real part is putting the data flow through the processing elements. So the flow part is the interesting part. The reason you want to do that is because you want to minimize I/O for the same amount of computation you do. So I wrote this paper, Why Systolic Architecture, in 1982. Yeah, that's right. I remember that time I wrote this paper when I was in California, actually, when I was working with TRW. They were interested in systolic array for obvious reasons, signal processing, all this stuff, radar, sonar, all this stuff. So it's really the I/O at the end is what makes the difference. So that paper become very highly cited. A lot of people read it because that paper about systolic arrays. Then, as you said earlier, when this Doppler sponsors us to build the war machine. It's a real piece of hardware. Actually, it was working. It's amazing. We were one of the few universities who could build hardware actually worked. We put the war machine on autonomous land vehicles. At that time we were doing the navigation automatically using very primitive machine learning. I still remember at that time, every time we want to do a demo to show how the robot follow the roads, we had to find a good time to do the demo. You know when it's a good time? High noon, when there's no shadows from the tree. Otherwise, the shadows would just be considered as the side of the road. Would never work. That time we were using the warp. We put the warp on this vehicle, robot vehicles or real vehicle later on. But anyway, that was kind of as a side. Okay, that was not that important actually at the end. The real important thing actually is the software, because the war machine, each processing element actually is a wide instruction machine. Because that time is already we're talking about VIW, we talk about this very wide instruction sets. It's kind of obvious. So of course you do a wide instruction set so that you can run all the I/O and the computation in parallel. We have so many computing elements on the processor we need to control. So we just use a very wide instruction to do that. So there's this VIW. I remember I was visiting Josh Fisher, all these people. A lot of fun at that time, intellectually a lot of fun. And then we start realizing, Monica Lam started realizing, not me, okay? She started realizing, all these systolic arrays operations for simple ones at least, this just a row of a loop, just a loop and rolling. Then the data dependency can be kind of down through data flow over systolic array. every cell is running on something different, but the previous cell's result can be used in the next cell. So this later is kind of become like the whatever they call the pipeline parallelism or whatever. Okay. Yeah, of course you do that. So the Systolic array for simple cases is just like a pipeline parallelism. And you can even automatically derive those. So once we realize that, then of course the more interesting stuff is software. So the software pipelining from Monica then become kind of really important at the end. And then in the meantime, I should remember that. You know, I wrote one of the first papers of parallelizing backpropagation in 1988.
Small world.
So and I was working with this AI guys. They were telling me this backpropagation is really important. You guys building parallel machine, you better help us to do that. So we implement that thing, simple ones at that time. So that paper actually was cited quite often now. I never remembered that paper actually after 20 years. Then suddenly occurred to me, I did something about that thing a long time ago, because now I have to know backpropagation really well. Anyway, so afterwards, you know, this thing, you know, there's this even those architecture probably called what decoupled access execute DAE kind of thing. They all kind of way actually in a way they can derive our Systolic arrays automatically. Okay, in a more flexible way, actually to put a queues between those execution unit and the data unit and so on. And then I mean the memory unit. We also in the meantime built something called iWork with Intel. That works too. Actually, it's amazing. The chips work actually. And then we built some experimental stuff called the programmable Systolic array, PSC, and so on. So after that, you know, I basically fed up with the field. I'll tell you why, okay? The reason is I find it's very hard to generalize the work. You know, typical approach we had is to put the Systolic array in a host environment, just like today. You know, today we're doing the similar things, but at that time the host environment is so bad, software is so bad. You don't get any speed up because all the time spent is in between the whole host and the Systolic arrays. Okay, and it doesn't seem that's an easy way out. Okay, and that and in the meantime, I started realizing that maybe all these networks between the processing elements really is important. I better know networking. I can't just learn those networking through computers. I better go to the computer networks field trying to learn from them. So I kind of left the field and went to computer networks. That was literally I left the thing in 1988, something like that. Just went away. And then, you know, what happened afterwards, I didn't even follow the field. People probably using the Systolic arrays. I know people telling me, you know, they were doing this, for example, in video encoding, they use Systolic arrays quite a lot. In sonar, radar, I knew they were using it because some people still calling me at that time. They build special purpose hardware and so on and so on. That was, but didn't interest me, all this stuff. Okay. Because I saw the problem was too narrow and it was not that interesting anymore. Then until Cliff sent me email in I think 2017, when your paper is going to appear. Then I start realizing the time is different now, because before I was so fed up with this special purpose stuff. Now special purpose stuff probably can be general purpose. You know, because if we can accelerate machine learning, and machine learning engine can be used in all sorts of different applications. So special purpose, general purpose approach. Now we suddenly life is totally interesting one more time. After that, I kind of start picking up the field again. Okay, I try to study computer architecture and trying to study software. Later, I even start entering scientific computing for the first time after 30 years. Okay, so talking about down data kind of stuff, how to do lim packet stuff, how to do matrix multiplications. I started out they are about the same actually after 30 years. Okay, they really need some help, I think, because the approach is more or less the same. Besides the machine is bigger, more bigger nodes, more GPUs and so on, but the methodology is more or less the same. So I think we can help on that. Okay, by bringing the new specs from machine learning, from computer science, architecture, and all this stuff. Anyway, this is just a side. So, but I start working on this. I start realizing I always go back to use Systolic Arrays. You know why? Systolic Arrays is so simple to think about. You don't have fancy instructions to deal with. You just have data flowing, going out. You actually can visualize the whole thing. So you can probably do performance evaluation more easily. You simplify the routing because routing is so simple. So I can predict what will be the FPGA's performance once I have a high level design. Otherwise, you never know. After you route the whole thing, maybe the performance will be so bad. But Systolic Arrays, you can be assured the things are not going to be so bad, okay? Because things are regular, wiring is short, all this stuff. So it becomes very convenient. I can do all sorts of optimizations, such as pruning, quantizations, without being not really sure the result will be, because the other part of the thing seems to be pretty much straightforward. Because so I always use Systolic Array as our vehicle, trying to do the implementation. Okay, so this becomes interesting. It's almost just for simplification. Okay, for example, we've been working on packaging stuff. For example, to see how can use the vertical connections connecting memory dies to logical dies. This kind of stuff, if you don't think about in terms of Systolic Array, it's very hard to visualize. You have to do something very simple, so you can see the geometry. You can see the walls or wiring situation, all kind of in your head before you start running the software, trying to see exactly how long the wire will be. So this become really convenient to me. So for me now I use Systolic Arrays just for the purpose of doing the design. Simplifications. I can tell you lots of challenges, but why don't I hear from Cliff?
No, that's a fascinating story, and I guess I'm very much interested to hear Cliff's side of the story.
I just loved all the different historical perspective and the interweaving of neural networks and matrix multiplication throughout your story. It's you didn't mention Cannon's algorithm, but Cannon's algorithm,
that's right,
is a predecessor of the matrix multiplication hardware around 80 or so.
Mm-hmm.
And now the HPC people have Summa, which is a generalization of Cannon. But Cannon and Summa and the matrix multiplication flow in a Systolic Array, they're all relatives. They're all kind of getting at the same sort of parallelism. So I feel like there's a it's a dialogue that we're still having today about like, where's the time going and how do I ship all these things around?
Yeah, because there is it's a good question actually. I've been looking at the summit lately. Yeah, now there seems to be this old story. Okay.
So I will say I met HT in 1991 or 92 when I was trying to pick a graduate school. And at the time he was leaving CMU and jumping to Harvard. My impression was that you had your DARPA funded empire and you were trying to get out from under it so you could actually do hands-on research and see students once again.
That's really true.
And so I think I actually interviewed with you in your CMU office and said, should I come to CMU or should I come to Harvard? And you said, if you want to work with me, come to Harvard. And I'm doing networks. And so I thought, oh, okay, he's this famous guy and I'll come and work with him and learn how to do networks. And I got to Harvard and worked on CreditNet with Bell Northern Research and ATM credit-based flow control for the first couple of years. And it was interesting because you had this reputation from Systolic Arrays, among other things. And you even brought an iWork machine to Harvard, which sat in our machine room. And I think almost nobody programmed it. And when I would ask you about the Systolic Arrays, you'd say, oh yeah, I'm done with that. Architecture is boring. Networking is where it's at, which is, your timing was great, right? It was 1992. The internet was about to explode. So I think I have to credit your taste there, but it was also closing the loop, really quite satisfying to go and join Google in 2013. And my colleagues here already knew about systolic arrays, right? The ideas are famous enough that, you know, the architects who I joined were already saying, well, if we've got a matrix multiplication to do, a systolic array architecture is the right thing to use for it. So it's not like people didn't know about it, but it was hugely satisfying to go and learn the stuff that in some ways I hadn't been paying attention to in grad school, right? Because we were worried about networks and contention and arbitration and priority.
never even mentioned once systolic arrays.
I think you did, but I think you said architecture was boring, as of 1992. And so this revisitation of systolic arrays in a different era was tremendously satisfying. I have some technical commentary, but I will say it was personally satisfying to hear from HT that when I sent him the paper that he had no idea that we were up to such things.
I had no idea.
And it was
actually at that time I knew very little about deep learning, so I couldn't even appreciate it. Anyway.
But okay, so Jeffrey Hinton didn't get to you because he spent time at CMU and he said he tried to get
I know
the CMU.
That Jeff Hinton, I kind of knew him okay. But he didn't talk to me because he was totally hiding himself up north in Toronto, working on his stuff. But he was really very good at CMU at that time. I already knew that. I'm not nobody to judge that, but I could tell. He was one that things makes most sense among all the AI folks.
So it was interesting to me to hear you talk about how systolic arrays simplified the I/O problems and improved the number of reuses of a data item once you got it out of the memory system, because the era you were working in, around 1980 or so, was a different era technologically. Like that's close to the Cray era, where compute was precious and memory was cheap. And so you get Cray designs where he's got this unbelievably multi-banked memory system, hero engineering on the super cheap memory to deliver a word per cycle to the vector ALU, and just one vector ALU in his pipelined vector execution machine. That was the fastest machine on the planet. I think it's really interesting that you were worried about the I/O in that era where I/O was cheap and compute was hard.
Yeah.
And now, of course, 40 years later, we've reversed things. And now memory is impossible and compute is unbelievably cheap, right? We got billions of transistors. How many ALUs, how many cores would you like? Versus there's only so many pins I can stick on a chip. There's only so much bandwidth that like physics lets us get onto the chip. And so the I/O stuff, you're once again too ahead of your time.
The reason is I was fed up with the host. It was very clear. No matter what we do with those accelerators, we're always bounded by the host. Host basically is where we have the memory.
Ooh, I should come back to that then, because there's a really interesting lesson in accelerator design about Amdahl's law, right? The standard thing, you build your awesome matrix multiplier or your awesome pairwise particle interaction module, and it takes the 90% task in your benchmark or in your application and makes it become 0, right? You throw hardware at it and it becomes 0, and now your maximum speed up is 10. Gee, was that worth all that heroism?
So very clear. Even then, the problem is going to bite us. That time we already hidden by that.
And the answer for our era, or for the current era, has been you have to put enough of the host-like things into the accelerator for the whole system to work, right? You can't go back to the host. The host is a PCI Express bridge away, which might as well be another continent.
That's right.
Right? All the GPU stuff in 2005 to 2010, basically, they would take a kernel and it would look great, and then they'd map the whole application and their speed up would be
right. So
and when they finally got everything on, right? When they finally moved all the code onto the GPU, then they got the great speed ups.
If you look at how many registers they got, it's just an insane amount.
Yeah.
But this is of course people are realizing that. But I still think those things are very expensive. They need to be, Then we need better methods, better memory hierarchy, better control. The thing I mentioned to you about getting into a scientific computing thing is basically it's about how to reuse local data. There's a famous algorithm called the GoTo algorithm. I don't know if you heard this thing.
For matrix multiplication on CPUs.
Yeah, for matrix multiplication, TPUs.
Memory system.
You do the memory systems. You play the same trick for each layer in the memory system. So this is the kind of things I think we should pay more attention to it. And I think the situation is not that good. GoTo stuff was invented a long time ago. We're not making much progress in the last 15 years.
Well, where's the bottleneck though?
The bottleneck is the methods. All these things are very ad hoc. It's not systematic. Of course, you can argue this particular algorithm in some sense is systematic because he played the same tricks for each layer. But I want the systematic across problems, not just a single matrix multiplication.
Okay, so generalization from the GoTo approach.
Of course, in real world, it's not just matrix modification. It's a little bit more than that, of course. Okay. Yeah. So we need to deal with this memory hierarchy much more seriously. You can't use the manual method to kill it. Like people like me, who just couldn't, just have to leave the field because it was no fun that time.
So there hasn't been that much invention on memory side in the last 30 years.
More or less the same thing.
Yeah,
that's the impression I have in the last year or so when I was going back to the scientific computing. They are very good indeed, but it's kind of like a lot of ad hoc stuff.
I agree about the ad hocery. It feels like there ought to be principles. There ought to be Mark Hill 3Cs hierarchy kinds of analyses, but for the way the data moves through your memory system, and that next step hasn't been a focus for us in, I don't know, most of my career. So where do we spend time optimizing TPU code? It's how do you shovel stuff out of HBM?
That's where we'll make a difference at the end.
Right, out of HBM into the on-chip memory, and how do you carefully marshal your only tens of megabytes or hundreds of megabytes of on-chip memory, because that's small these days, to maximize on-chip locality. We have these 100 teraflop matrix multiplication units, but keeping them fed, right? That's where the invention is. So
that's right.
I'll throw my soundbite in. I think there's a, I forget which general it is, says good generals study strategy, great generals study logistics.
That's right. And they want to make sure the supply line can be kept up.
And I think the same is true in computer architecture, that good architects study computation, but great architects study choreography.
Yeah, choreography, the orchestration of the data flow, of the local, what you keep locally, what you kind of pull them away, the kind of things. Okay, it's really about the scheduling at the end. Maybe, I don't know, there's a whole bunch of ideas there indeed. So this already getting into challenges, okay? I think we're already in this, in the next part, the challenges.
Yes. So to summarize the discussions, at least what I understood at this point, I guess we talked about two main challenges. First is the communication between the host and accelerator, and the second one is the memory bottleneck. Given that we are at the end of Moore's law and we have to specialize to extract performance, so how do you see our hardware change over time, like in 5 years, in 10 years?
I think we're already seeing 3D comes in, all the high performance, high bandwidth memory stuff, from NVIDIA, all this stuff. They are 3D or 2.5D already. It's just matter time. Those stacks will be more ambitious. So stack of dice, okay. And now we have a real issue. Now we have to orchestrate the flow, not just on a 2D service. Have to orchestrate them through 3D. Okay, I don't think we even know how to think about this stuff. Definitely we don't have CAD. We don't have a CAD system to help us to do any of this stuff.
I think you're underselling your own history, HT. The matrix multiplication algorithm is fundamentally 3D. And part of the brilliance of the matrix multiplication systolic array is casting it into two spatial and one temporal dimension in a way that everything still worked out.
Right.
So, I think you at least have been visualizing in more than 3 dimensions for a while. And maybe our tools haven't caught up, and our fabrication hasn't caught up.
Actually, that's a real good question. That I think that one of the most use of AI will be in CAD in the next several years, and we probably need those CAD to do the next generation computers, to design next generation computers, because we have no clue how to design 3D stuff in general. How do you line up your memory module with your PEs upstairs? I'm not sure how you do all this stuff. We had a hard time even for 2D routing. If you don't have regularities in place, and 3D routing, you have to even stress the regularity even higher, even more than ever. I/O becomes an even bigger issue, right? You cannot get into the middle of the stack. You have to go through from the bottom die.
I mean, the scaling properties look daunting, right? Mm-hmm. Quadratic communication with cubic volume to do the work in, but doesn't that sound familiar? I mean, it's the same in 2 dimensions.
This is linear. The whole, the thing I mentioned to all these things. At the end, we're playing the maximize the surface game given the volume of computation we need to do. Indeed, this is that's the paper that we just wrote, which is going to appear in SC21. The supercomputing one is exactly about that. It's trying to maximize the service for the same amount of computation you do.
I need to ask you about that or read that paper, because that's the opposite of the direction I would have guessed. The thing that I think is lovely about matrix multiplication.
I just said opposite. I think it's to minimize the surface for the maximum computation you do.
Good. Okay, that I buy.
I was wrong. Yeah. So usually that happens when you have a square, have a perfect cube. But in reality, you don't have a perfect cube for all sorts of reasons. You're tiring, or depends on your matrix sizes, all this stuff. So
well, the tiling might help save you. The tiling might get you back to more
tiling. When you want to map anything on a small fixed size hardware, you have to tile the matrices into small chunks. Those tiles have to match with your original matrix sizes, especially for small matrices. That's another thing we're learning. You know, most matrix modifications actually among small matrices.
Yep.
It's not those asymptotic big matrix stuff people sometimes comment on. It's not. It's a whole bunch of small matrices. And small matrices, those shapes become really important because any padding you do to pad a matrix to be of the size of the multiple your hardware size, this padding relatively become important when the matrix is small. You can easily lose 50%.
Oh, 97%.
It's 50%.
No, you can lose 97% if you're.
You can lose 97% even. Wow.
So the first TPU has a side length of 256.
I see.
But our convolutional inputs were RGB, which is 3.
Oh, RGB is terrible. The first layer is terrible. Yeah, I agree.
Out of the box, our default utilization would have been bounded to 256.
You guys have a special thing there.
Yes.
In order to do the RGB is the only 3 channels you have to deal with that. Yeah. That kind of issues we do have to deal with. So this stuff is, but on the other hand, I find that those scientific computing guys are very strong in SIMD.
Yep.
They've been working on this for a long time. They certainly have good software for that. But on the other hand, I would like to see we can translate this SIMD stuff into Systolic arrays. It shouldn't be that big a jump. Okay, if you can program your SIMD machines, I can translate your C++ code into a code probably for Systolic arrays. Probably I can do that because you have done the most difficult part. Is namely how to partition your matrix into chunks that can work on SIMD arrays. Once this is done, we can do the next step. Map to SIMD or map to Systolic array is a kind of a local problem. So
right, then it becomes an implementation technique.
Yeah, it's just local. It's not that bad anymore. I can use go-to algorithm.
So I have a different direction to go with Samira's question about the end of Moore's law and where we go with accelerators. And I think my observation is an admission of failure so far in my career that I've managed to build a couple of interesting accelerators, but they're both really hard to program. Like they're just kind of awful. Like you gotta get your not just hero programmers, but like superhero programmers to write code for these horrible things.
But on the other hand, look how many armies people in NVIDIA they have in assembly code their GPUs.
I have hope.
It's insane as well.
I have hope about the future of architecture because at the end of Moore's law, a single core, a single thread of control is unbelievably small.
Yeah.
Right. Like how many cores can you fit into a square millimeter today? Right. So if you're commissioning your accelerator, your giant systolic array for whatever your application is, and it takes up tens or hundreds of square millimeters, then adding a general purpose control thread to it is actually not necessarily that hard. And so, why should you reinvent the general purpose computer when people will sell you a general purpose computer that's a corner of your die? right? Why not just use the solution that people are already providing and hybridize? So I feel like there's a dialogue. What's the term I'm looking for? There's
probably, yeah. There's a new way of looking at this thing. Yeah, probably. Yeah, I still have faith. I think we probably already. It's a lot to do with our point of view. It's rather than inherent. That's in some sense that's something we really need to fix. No, it's rather than some things really hard we cannot fix. Okay, but certain things like along the lines you say it's not necessarily that much work.
Right.
It's really the direction is more important. Yeah.
So I guess students who are kind of looking for new problems for their research or trying to figure out new use cases. So what would you suggest? Like what problems they should
along all the lines, you know. Let me. There are a couple things probably is also we want to pay attention. You know, I talked to these scientific computing guys once for a while. One of the big problems they have is embodied problem they always have, because only the embodied simulation they can get the real thing. You just do statistics about how many particles in certain type you have. It's not enough. They want to know how the particle moves. They really want to do the details. Then you need an embodied simulation. You know, look what embodied simulation doing is just a whole bunch of pairwise dot product. Systolic arrays can do that, of course. Why we didn't do it, I don't know why.
I guess Cliff already mentioned the programmability challenge, how to make the accelerators more programmable.
Yeah, you know, this embodied problem, the I/O problem is not that bad because the computation is so much. So relatively speaking, the I/O time is not so critical. Unlike the kind of machine learning powered problem, embodied problem really is purely computation. But even for that,
I was going to say I don't know how to make a scale-free n-body machine though. Right, like
Anton
Anton machines.
Anton machines for any number of particles to scale up to any. Okay, that I probably know what you're saying. It's the issue is about the partitioning.
So if you look at Anton machines, they were the first generation was designed for 50 to 200 particles per node in a 512 node machine, and if you got beyond that, you started running out of the precious SRAM, and once you fall out of SRAM, you're back to the memory problem.
You're dead. Yeah. So you in a way you're right. I was thinking is that the whole thing can be hosted on one computer node. Okay, if you can, then yeah, you need to deal with many particles. Then I agree. You go back to the old I/O issue.
So do we have any supercomputer with systolic arrays? Not yet, right? Like at least.
Yeah, I'm saying you should able to think about that by replacing SMD with systolic arrays.
Yeah.
I'm thinking whether I would call Anton's a systolic array, and I think inside of the pairwise particle pipeline, that is a very much domain-specific systolic array where the 50-odd operations of what's the force of this particle on that are just mapped into perfectly pipelined code. Two positions come in and two potentials or the relative force comes out.
I think the point is every vector of the particle vector is going to be doing a dot product with every other particle. So this is really is a matrix the modifications, with the second matrix be the transpose of the first matrix.
So would anyone be able to map this algorithm on TPUs?
On TPUs has not been used for systolic arrays. TPUs it's literally just doing the SIMD. Yeah.
Say that again.
TPU implements SIMD parallelism.
It depends on which level. I mean, I think
Yeah,
across
the
the nodes in the pod.
high level, you do the data parallelism kind of stuff, which is kind of course, I'm saying the low level parallelism is SIMD.
So currently the programming interface that is exposed, I believe we should be able to map matrix multiplication type of programs on TPUs. Is that correct?
Actually,
but the reason they don't support Systolic Arrays well, even you want to try, is because they don't have good neighbor connections between their cores. The cores are organized in some memory banks, but it's not a general grid with neighbor connections.
Let's see, two different directions to go. So there are some intrepid people doing scientific computing on TPUs. Yifan Chen's group at Google has been publishing papers. I just saw a computational fluid dynamics one go by, but they kind of are using the TPU as a giant brute force matrix multiplication machine. So if you can state your CFD algorithm in terms of matrix multiplications, then the TPU is just a great machine for you to use.
Yeah, that's right. That's absolutely. They have been using an SMD method, not Systolic Array.
Yeah,
that's all I'm saying. They do matrix modification in a very serious way, of course. Mm-hmm. The issue, the open question is if some of those scientific computing stuff can be done on Systolic Arrays.
Right. Well, and going way back in the discussion, the thing that TPUs don't do, especially right now, is the general purpose networking. Right. We're very good at regular networking in the interchip lines, and like if you do an all reduce or a regular all to all, that maps pretty well. But the sort of ragged contended traffic of random access, that you kind of need that for some general purpose scientific codes, and that isn't something we've focused on as much.
I've been proposing using something like H tree. You heard H tree?
I'm not sure.
H tree is like a tree. The middle of it's basically the tree. You just draw an H, the letter capital H.
Ah, okay. I have seen those, right? So that's sort of hierarchy.
Recursively
yep.
Make a small h on the leaf of the big H. At big H, you have four leaves. Then each leaf you can spawn another H with four leaves as a subtree of that leaf. So H tree wouldn't be that expensive, but still can kind of balance between global communication and local locality. That's something is in the middle. It doesn't need a really very expensive interconnection networks, but it's more general than a neighbor connection or a torus.
Yep.
A torus is great if everything's a neighbor, but once for a while you need a long distance connection. You're going to take many steps, but you build a tree on top of it. It's not that bad. I've been thinking about that.
So one reason TPUs became viable because there is so much demand from the machine learning community, and people just are coming up with bigger and bigger models. So in terms of other fields, like when we talk about scientific computation, like there may not be that much of demand. So do you see like future accelerators, maybe more general purpose systolic arrays for other types of special computation? Like, is that something would be viable, or do you think we actually need something?
Embodied is a classical example in that field. Okay, and there are lots of simulations people have to do to simulate physical behavior. Actually, machine learning eventually has to work together with science for obvious reasons. And so we need to use simulators to generate synthetic data to train models. This simulator currently running like 1 million times slower than AI models. Okay. We need to find something in between, okay? So whenever we can speed up, we should speed up, somewhat, but it cannot live with the current way of doing things. Using the physical simulators to do the brute force synthetic samples generation. It takes too much. It's not useful. So we have to get the machine learning and the scientific computing guys working together, which for us is good because we don't totally go away from the machine learning field. So we can kind of play our own strength a little bit. In the meantime, we can start talking to the physical guys, and they have physical insight we need to leverage so that our trained model will have some real physical meanings. So that line of work, I think we have opportunities, but we do have to broaden ourselves a little bit. Maybe solve 3 equations in chemical engineering. Now, the chemical engineering for the last 50 years, they always have 3 equations forever.
I guess I'm kind of not aware of what's going on in chemical engineering, but that's a very good insight that.
But that means we can really help.
Yeah. So Cliff, I guess, yeah. What's your feedback on that?
So I agree with HT about hybridizing ML, not just with HPC, but with everything. I've drunk the Kool-Aid, but I think that ML is general purpose data-driven decision-making.
Yeah.
So any place you have an if then else in your code is a target for ML. It may not be cost effective now, but as we get better at ML and we build the hardware to make ML decision-making binary classifiers cheaper, it's going to become a target. And in some ways, like at the lowest level of our hardware, we already have it, right? What's a branch predictor? It's a machine learning device that learns and predicts in a single cycle. So right now, our ML models take a millisecond to calculate. So is that 1 million clock cycles? So that's 6 orders of magnitude off from a branch prediction, but there's a whole span there where you could simplify the model or change your problem domain. And again, as we get better at this, I expect that all sorts of decisions are going to become ML accelerated. I also wanted to, go ahead.
Yeah, please.
I wanted to put my computer architect hat back on and say,
okay.
I got to build the Anton machines, which are an n-body problem machine. I got to build the TPU, which is a systolic matrix multiplier machine. There are other classic problem domains who haven't gotten quite as much love. Like I personally am very fond of the fast Fourier transform. And of course we know that there are fast Fourier machines you could build, right? Beautiful, there was a BDN butterfly machine back in the day, but is it time to bring butterflies back? Fourier is so unbelievably useful in so many domains.
Everywhere, yeah, I agree. I wrote a paper a long time ago, basically arguing the FFT IO problem is hopeless. You can prove it's hopeless because by definition, you only do log n operations per IO.
Yeah.
Log n is a very small number.
It's still got a little bit of that volume to surface.
A little bit you can use.
Again,
but what we have to do there, I think, is not using our computer digital thing. We have to go to analog.
Optical in particular?
Optical is a possibility because they can all do Fourier transform.
Yeah.
Okay. But the problem right away there is the A to D issue.
Yep.
I've been looking at the ping array, the processing in memory stuff, which actually I kind of really think they are really important. because I just have this terrible feeling that after 20 years, we realizing all the accelerator we build never catch up the machine learning demand unless we can leverage analog computing. Then there's a chance we can catch up again.
I guess some of the students who are listening, maybe they will pick up on analog.
Yeah, and analog. The good thing about analog is that the US is putting a lot of money into it now. All the global competition, there's a geopolitical competition means US putting $50 billion in 5 years, which I was told is a small amount compared to China is putting in semiconductor in all the hardware stuff.
Yeah, I guess we are kind of out of time. So thank you so much for actually telling us about all the cool history and how Systolic Arrays came by, and Cliff sharing his thoughts and his insights. Thank you so much, and hopefully we will sync up again sometime soon.
You're welcome, and thank you for having me. I'm happy to talk to you guys.
Thank you for hosting, Samira. And HT, great to get to chat. We should do this more often.